Did you know that, on average, every in-service aircraft is struck by lightning at least once a year? Despite the immense power of these strikes, the impact on the aircraft is usually minimal. In today's video, we'll explore how the A320 is built to safely handle lightning and the advanced safety measures that ensure these electrifying events are contained. Welcome back to A320 Knowledge, your trusted source for Airbus expertise. Today, we're diving into a tutorial on lightning strikes. In today's tutorial, we'll explore the following: how lightning strikes interact with aircraft and why they're more common than you think, the specific zones on an A320 that are designed to handle lightning impacts, and the incredible safety systems Airbus has built to handle high-energy lightning hits. First, let's understand the science behind lightning itself. Inside storm clouds, thermal convection causes ice particles to collide, which transfers electrons between them. This process builds up electrical charges within the cloud. Once the tension between charged areas gets high enough, it can overcome air's natural insulating properties, leading to a lightning discharge. Lightning can occur in three main ways: between clouds, within a single cloud, or between a cloud and the ground. Here, you can see the different types of lightning illustrated. Lightning bolts are immensely powerful. They start as a column of ionized air, known as a leader, which usually moves from the negatively charged part of a cloud towards a positive area. As these leaders progress, they connect with secondary leaders. When these connections are made, a significant electrical current flows, neutralizing the charges. A single lightning bolt can reach up to 200,000 amps and temperatures as high as 30,000 degrees Celsius. On average, Earth experiences about 44 lightning strikes every second. However, the distribution of these strikes varies greatly by region. On average, the global frequency is around 3 strikes per square kilometer per year, but certain areas see much higher rates. Central Africa, particularly the Congo Basin, stands out as one of the most lightning-active regions. According to studies by NASA, it can experience over 70 strikes per square kilometer annually, with some localized areas seeing peaks of up to 158 strikes. This intense activity is driven by the region's warm and humid climate, which creates the perfect conditions for thunderstorms. In contrast, oceanic regions, especially in the South Pacific, and the polar areas experience much lower frequencies, often less than 1 strike per square kilometer per year. This difference is due to the cooler, more stable atmospheric conditions over these regions, which are less conducive to thunderstorm formation. Here's a global map showing the annual lightning strike frequency. As you can see, the warmer colors highlight areas with the highest concentration of strikes. Now let's talk about how lightning affects aircraft. Statistically, each aircraft should be struck by lightning only once every 1,000 years based on surface area. But in reality, in-service aircraft get struck once every year, or roughly every 3,000 flight hours. Why? Because when flying near a storm, aircraft can actually attract lightning due to the high electrical fields present. This image shows how lightning interacts with an aircraft in flight. Lightning leaders can initiate from the aircraft's extremities, like the nose cone or wingtips, and connect to nearby lightning leaders, making the aircraft part of the lightning channel. Aircraft like the A320 are designed to handle lightning strikes without compromising safety. The entire structure acts as a conductor, allowing electrical currents from lightning to pass through without causing significant damage. To ensure safety, even composite materials have metallic foils and strips integrated into them to maintain electrical conductivity. Bonding leads connect all structural parts, allowing currents to move smoothly across the aircraft. The direct effects of a lightning strike can include burns, holes, and pitting on the metal surfaces, and potential punctures or fiber damage in composite parts. These effects are usually limited to the entry and exit points of the strike. Lightning strikes often involve multiple swept strokes, where attachment points move along the aircraft's surface. In addition to direct effects, electromagnetic fields from lightning can induce unwanted currents in aircraft wiring. To counteract this, aircraft are equipped with protective measures like shielding, electrical isolation, and surge arresters to prevent disruption of critical systems. As part of their design, aircraft are divided into specific lightning attachment zones based on how likely they are to be struck and the potential impact of a strike in those areas. These zones are crucial, especially for aircraft like the A320, as they guide maintenance teams in inspecting and repairing any lightning-related damage. Let's break down each zone to understand their significance. Zone 1. Initial entry and exit points. These include extremities like the nose cone, wingtips, and tailplane, where lightning usually strikes first. These areas are designed to withstand direct impacts. Zone 2. Swept stroke areas. These are surfaces like wings and the fuselage where lightning can move along as the aircraft flies. Due to the aircraft's motion, multiple strikes can occur here, known as swept strokes. Zone 3. Hang-on points. These are found on parts like the horizontal tailplane where lightning may stay attached longer, leading to sustained exposure. These areas are reinforced to handle prolonged electrical contact. By categorizing these zones, maintenance personnel can prioritize inspections, focusing on high-risk areas first. While direct lightning strikes can cause visible damage to an aircraft's exterior, the indirect effects can be equally concerning. When a strike occurs, it generates powerful electromagnetic fields that can induce unwanted voltages and currents in the aircraft's wiring and systems. To safeguard against these potential issues, aircraft like the A320 are designed with several layers of protection. First, system redundancy ensures that critical functions are duplicated, so if one system is affected, a backup remains fully operational. In addition, these redundant systems are physically and electrically segregated, minimizing the risk of simultaneous failure. The electrical harnesses are equipped with electromagnetic shielding to block interference, and in particularly vulnerable areas, additional shielding and specific routing strategies are used to enhance protection. Surge protection is another crucial element, with lightning surge arresters and electrical isolation techniques in place to prevent sudden voltage spikes from damaging sensitive components. Finally, sophisticated system software is designed to detect and manage any corrupted data, ensuring the aircraft's critical systems remain functional, allowing for a safe and uninterrupted flight. Flight crews are trained to avoid areas with high lightning potential using weather radar systems, ATC guidance, and forecasts. Newer radar systems can even predict lightning-prone areas, helping pilots navigate more safely. The Honeywell Weather Radar System, for example, can predict rain, hail, and lightning zones, aiding pilots in their decision-making. On the ground, safety measures are crucial to protect both personnel and the aircraft. Aircraft are grounded using low-resistance cables to safely channel electrical discharges away from the structure. Without proper grounding, lightning could exit through parts like the landing gear, risking damage and injury. During storms, maintenance activities are often suspended, as even grounded aircraft can still pose risks from shockwaves. External equipment, such as power units, are disconnected to prevent surges, and ground crews switch to hand signals to avoid using metal headsets, reducing the risk of electrical conduction. When an aircraft is struck by lightning, flight crews must make a logbook entry so maintenance teams can perform necessary inspections. The team gathers data from the crew, including any system malfunctions or alerts triggered during or after the strike. Depending on severity, various inspections may follow. A standard inspection checks the entire aircraft and its systems. If time or resources are limited, A quick release inspection, or QRI, focuses on areas most likely impacted by the strike, allowing the aircraft to continue flying for a set number of cycles before a thorough inspection is needed. For the A320, a QRI permits up to 50 or 200 additional flight cycles based on the aircraft and inspection results. If no significant damage is found, this flexibility helps airlines maintain operations while ensuring safety. However, if another lightning strike occurs during the grace period, a new QRI is required, though the cycle limit remains based on the original event. This process ensures safety while optimizing fleet availability. To wrap things up, while lightning strikes may sound like a dramatic threat to aviation, modern aircraft like the A320 are expertly designed to withstand these forces, with robust safety features that ensure passengers remain safe. From strategic materials and lightning zones to advanced radar systems and thorough inspections, aviation has perfected the art of flying through electrifying storms. Our popular A320 tech quizzes are now part of an exclusive newsletter membership designed to provide you with even more value. As a member, you'll receive 4 brand new A320 tech quizzes every month, one each Monday, delivered straight to your inbox. You'll also receive exclusive deep dives into A320 systems, procedures, and techniques that go beyond this YouTube content. And you'll also gain access to bonus content and other surprises to keep your knowledge fresh and up to date. If you're interested, click the link in the description or scan the QR code on screen to sign up today. Thanks for tuning in, and let's take your A320 knowledge to the next level.